Hello everyone. In this episode, I spoke with Jagdeep Singh, the CEO of QuantumScape. We spoke about the technology behind solid-state batteries for EVs and how material science is crucial for finding the right solution for not an easy problem. One of the important features for QuantumScape's solid-state battery is the charging as fast as internal combustion engine, taking into account safety, cost, and life cycle, and the challenges of scaling up. We also spoke about the competition, criticism, and QuantumScape vision in the long run. I am Marwa Dwini, and this is the Soft Robotics Podcast, and here's my interview. Thank you. Hello, Jagdeep. Thanks so much for joining us in the podcast. Such an honor to have you. So I would like to ask you first how you would like to define yourself for the audience who may be first time listening to you. How would you like to define yourself?
Well, I think of myself as basically an entrepreneur, and we're interested in trying to solve, problems that we think are important in the world. And right now, this problem of emissions and climate is one of the most important problems that we think we face. Some of our investors, for example, John Doerr of Kleiner Perkins, thinks it's the single biggest problem facing humanity. So we started the company to try to address that particular problem. One of the biggest emitters of greenhouse gases is of course, the transportation sector, combustion engines. So we chose to focus on that sector, and we saw that battery powertrains, really are not very competitive with combustion engine-based powertrains. So our mission really was to try to improve the battery, make a better battery that could narrow that gap, and in the process increase adoption of electrified powertrains and make an impact on emissions. That's a quick summary of what fundamental motivation was.
Great. So before going to that question related to that part, I'm curious about your childhood. How was your childhood? Do you remember any memories about being interested in what you do now? Any memories about that?
I mean, my training was in computer science in college. But as a kid, I was always interested in physics, and I never studied it, in school. I did do undergraduate degree in computer science and a graduate degree in electrical engineering. So there's a certain level of physics that you get in a double E program, but I never studied physics, professionally. So this actually feels it's really fun because a lot of what we do is fundamental physics. I mean, the chemistry and the behavior of these materials at a basic level. So, I'm very much enjoying the opportunity to get, deep into the weeds of how, physics works at the materials level, and how we can solve real problems with that.
Great. So I'm curious for the start, when you started QuantumScape in that case, it was a risky idea to go for a problem that you already mentioned many times. It's really hard problem, and still there's lots of challenges. It was risky for you how you just approach the idea like solid-state batteries. Maybe if you tell us how it was, and since it was risky, maybe, I don't know.
Yeah, no, it was without a doubt risky. I mean, when we started the company, all we knew was we wanted to make a better battery, and that meant that we wanted to get, a lot more energy density, around 1,000 watt hours per liter. And we wanted to be able to fast charge batteries in a lot less time than batteries at the time required. But we didn't have a particular religion around which technical approach was going to be the best approach. In fact, the initial approach that we started with, we quickly realized was probably not going to be as practical as we'd like. So we switch to a different approach, which is the approach that we're currently pursuing, 10 years later. And when we started the company, we told our investors up front, we said, look, this is a high risk, high reward play. We don't know if this is going to work, but if it works, we think we can make a big impact. Luckily, our investors were, venture capitalists that had already made a big impact in their previous projects. For example, two of our Series A initial investors were John Doerr and Vinod Khosla. And John, you might know John Doerr. John is, probably one of the most amazing investors in the history of venture capital. He was the initial investor in Google, and Amazon and Netscape and Intuit and Sun Microsystems. That's amazing. I don't know of any other single investor that's done that many deals. John was interested in making a big impact, and he was comfortable taking a certain amount of risk. Vinod was the same way. He'd been on a number of iconic companies as well. And both these guys had room in their portfolio for a company that was, high risk, high reward. And that's where we kind of fit in. And luckily, we were able to build a fantastic team of people, raise a lot of capital along the way, hundreds of millions of dollars, get, great support from the automotive OEM customer base, including, for example, Volkswagen, that's our biggest partner. And all those things put together allowed us to actually execute and deliver a chemistry that, in fact, does enable a solid state approach to batteries that then has the potential for high energy density and fast charge and safer operations. We're not done yet. I mean, what we've shown is that the chemistry works. We've shown data on that front, obviously. But what we haven't yet done is scale it up into mass production. And that's really the challenge we're currently focused on. Is now that we've shown that there exists a chemistry that is solid state that you can use with lithium metal that delivers, that has the potential to deliver all those metrics of high energy density and fast charge and safety and so on. Can we now mass produce that? And that's a non-trivial challenge, but that's our current focus.
Wonderful. So before going to the scaling problem, maybe I'm curious about the trade-off between the current batteries, lithium-ion and electric vehicles, and the solid-state one.
At the core of the electric powertrain is, of course, the battery, right? And batteries today have a number of limitations that impact the vehicle performance. So one is they don't have enough energy density. And energy density is, of course, translates into driving range, right? So how many miles you can go on a single charge. The second limitation is power density, how quickly you can extract or put back in the energy into that battery. That translates into charge time. So today's batteries take about an hour roughly to get to 100%, maybe 40 minutes to get to 80% charge. A combustion engine-based car might take 5 or 10 minutes to refuel with gasoline or petrol. So that was an issue with batteries. There's safety issues with today's batteries. The electrolyte that conducts lithium ions in the battery is a hydrocarbon. So it's basically a fuel that can burn. Even if the battery is fully discharged and has no energy in it, the electrolyte itself can burn and result in an explosion. The cost of the battery is much higher than the combustion engine is today. It can cost many thousands of dollars for the battery pack for any kind of decent range. And then the cycle life of the battery is also limited compared to combustion engine. So those are the 5 key limitations of lithium-ion batteries. It turns out you can solve all 5 of those if you switch the chemistry from a carbon-based anode, which is what's used in today's cells, to a anode made of pure metallic lithium. Now, that's been known for many decades, but the problem has been that it's been known that lithium metal anodes don't work well with conventional liquid electrolytes because lithium is very reactive. And as a result, you have 2 problems. One is a chemical side reaction of the liquid that results in impedance growth. And the second is formation of needle-like crystals called dendrites that can short circuit the anode and cathode and cause a failure. So to make lithium metal work, you need a solid state separator or electrolyte that allows lithium ions to go right through it like a highway, but stops lithium metal dendrites like a wall. And that's been the fundamental challenge holding up the whole industry for many decades. And that's what we set our sights on achieving. That's what we're excited about in terms of the data we've shown is we've shown that we've got a solid state separator that enables a lithium metal anode, which in turn then allows you to build a battery that has more energy density for greater range, higher power density for faster charge times, safer operations because there's less flammable content in there, better life characteristics, and in fact lower costs because you simplify the cell by eliminating the conventional anode. Now, our design is an anode-free design, which really allows you to be lower cost. So, long answer to your question, but the quick summary is that the solid-state lithium metal architecture delivers a number of key benefits over conventional lithium-ion architectures. which in fact make it very relevant for this EV transition.
Great. So I guess just in that case, what could be the missing pieces? Maybe if we speak about scaling up, or also you can pinpoint about maybe what is maybe the question that leads you to answer the transition from, for example, to solid state. Is it the material, structure, or I don't know if you can reveal about that.
Yeah. So the key really is the material, the solid state separator material that we've made. People have looked at many different classes of material over the last, again, 40 plus years, but none of them met the core requirements. In particular, none of them met the requirements of preventing dendrites. Even today, there are many other solid state approaches that are out there. People are using sulfide-based separators. People are using polymer-based separators, oxide-based separators, but every single one of them that we've seen results in dendrites. Now, if you have dendrite formation, you can still make cells and run them if you compromise one of a couple of things. You can either revert back to a carbon or silicon anode as opposed to lithium metal anode. That'll prevent dendrites. But then you're no better off than today's lithium ion batteries, because you just have the same architecture as lithium ion today. Or you can compromise the test conditions, run these batteries at lower rates of power or higher temperatures or for a shorter number of cycles. But any one of those three things makes your battery not practical for real EV use. So the challenge has been to make a separator that's solid state and can prevent dendrites under uncompromised test conditions. That's what we did. And then in December, you might have seen we showed a number of results that made clear that the cell can cycle for up to 1,000 cycles with something like 90% capacity retention, which is above the spec of 800 cycles to 80% capacity retention. We showed the ability to fast charge. We showed the ability to work at low temperature. So all those were really key breakthroughs. All that's been shown with actual data that we published in December. Since then, what we have focused on is taking that single layer cell. Single layer means it's one cathode, one anode, and one separator, and stacking those single layers up into a multi-layer cell. The multi-layer cell allows us to increase the capacity of the cell, the amount of energy stored in the cell. And the multi-layering problem involves no new chemistry, right? All the chemistry is encapsulated in that single layer. So there's no new materials and no new interfaces that are introduced when you go to a multi-layer cell. But you do get more energy. So the interactions are, when you stack the layers up, you have more mechanical interaction and electrical interaction. These layers are connected in parallel electrically, but no new chemistry. So we've been working on that. We announced that we had made 4-layer cells on our last earnings call, for example, and the behavior of those cells is very similar to what we saw with the single-layer cells. But that's just the starting point. We now need to stack up to 8 to 10 layers. Our goal for that is end of this year. And then by next year, we are targeting being up in the dozens of layers in these cells. When we get up to dozens of layers, that will be what we call the commercially relevant form factor. That will be what we intend to actually put into cars. But even after we make those multiple dozens of layers, we still need to basically be able to scale up the production capacity of the process, be able to make thousands and hundreds of thousands of cells, so we can put them into cars. Each car takes about 1,000 cells, so you need a lot of cells to get a lot of cars. And then we need to keep improving the process here. We need to, there's work to be done in terms of making the process, more consistent, so we can, have less variability in these cells. Making it more uniform, higher throughput. Those are all things we have to work on as part of the process. So a lot more work to be done, but the fact that we have the core chemistry means it makes sense to do that work. If we didn't have the core chemistry, it would have made no sense to try to work on scaling up a chemistry that doesn't work, right?
So I'm curious, you mentioned many interesting points. Do you think that maybe reproducibility of this kind of behavior or of the cells will be different? Do you believe that if you have like dozens of layers, or I don't know what kind of anticipation, what could be different? I don't know how you anticipate the process would looks like, or challenging.
So as I mentioned, when you stack multiple layers up, there's no new chemistry involved, and all of the behavior of the battery really comes from the chemistry. So the energy density, the charge times, the safety behavior, the resistance of the cell, all those characteristics are a function of the chemistry. So the fact that you're not changing the chemistry leads you to expect that there should be no changes, no fundamental changes in behavior as you stack them up. And that's exactly what we saw when we made the 4-layer cell. So the 4-layer cell that we showed data on, the cycling behavior was very similar to what we saw in the single-layer cell. It's just that it had 4 times the capacity. And that's what we expect going forward as well. Because all the chemistry is in that single-layer cell, we don't see a fundamental change in behavior. We don't expect to see fundamental change in behavior as you stack these up. The challenge there is simply, can we reliably stack up these layers, have the right level of alignment between the layers, have the right rate of stacking in our stacking tool so we can make enough of these cells. Those kinds of challenges, which are more manufacturing and mechanical engineering related, as opposed to fundamental chemistry.
But I'm curious, in that case, do you have kind of limitation, or maybe, I don't know, through that trials, I don't know if you have any kind of downside or limitation so far, or I don't know, have the kind of redundancy in the design so that if there's failure, I don't know, it's still, this battery can function?
Well, our target is to make every layer extremely reliable. Batteries are, batteries for cars are systems where reliability is paramount. You have human beings sitting in cars, right? It's not like a cell phone where if the cell phone blows up, a human being isn't sort of trapped in the cell phone, right? Maybe they get burned or something, but if you're in a car, safety is really, really important. So our target is to get to a very, very high level of reliability. That said, when you have a multi-layer cell with dozens and dozens of layers that are connected in parallel, if there's a problem with one cell, because they're arranged in parallel, the remaining current is distributed across the other layers in parallel, and so there isn't necessarily a huge impact, but more importantly, our target is to get a very high level of reliability on these cells. So you can't really rely on redundant systems. In our view, we just want to make sure that the cells are fundamentally reliable.
And I'm also curious about the charging time, because you mentioned that, of course, it reduces, but I don't know how you can see that pushing the limits of charging time with the design of the stack this many layers. Do you think that's a limitation, or you can make the charging time just as fast as a combustion engine?
Yeah. So what limits your charge time in a normal lithium-ion battery is I guess there's 3 things: the rate at which your cathode can deliver lithium ions into the electrolyte. That's 1. 2 is the rate at which lithium ions can transport themselves through that electrolyte, which is the medium through which ions move. And 3 is the rate at which lithium ions can diffuse into the anode particle, which is the anode side, the negative electrode. Now, in a real battery, the third thing is the key limiter. The anode, the rate of lithium ions going to the anode is what limits the rate of charge. If the rate of diffusion into the carbon particle that makes up the anode is a fundamental material property. You can't change that by trying to charge it faster. If you try to charge it faster than the lithium ion diffusion rate, what happens is, instead of diffusing into the carbon particle, the lithium ion starts plating on top of the particle. Think of it like a snowplow effect. And then it forms those dendrites that I mentioned earlier, which short circuit the cell. So when you fast charge a lithium ion conventional cell, it's kind of a dance between charging as fast as you can, but not so fast that you tip over into the dendrite regime. That's the limitation today. In a solid state lithium metal battery, you do away with the carbon anode completely. So now, instead of having carbon anode, there's no anode, and the anode now is formed of pure metallic lithium that's coming out from the cathode when you charge it up, which means you eliminate the diffusion bottleneck. So now you can charge the cell as fast as the cathode can deliver ions to you, and we've shown in the data that we published that allows us to charge in 15 minutes. 0 to 80% in 15 minutes is what you get with a lithium metal cell. which you can't do with conventional lithium-ion cells because of the diffusion bottleneck on the anode side. So that we've already shown, and we obviously need to improve the reliability of that and the uniformity of it, so we can do it every single time. We've shown that the fundamental chemistry enables that. So 15 minutes is not the same as 5 or 10 minutes, like a combustion engine-based car, but it's a lot closer to combustion engine than today's batteries can get.
So maybe before going to other question, I have one question. I'm curious about the competition in that case, because I don't know how it for you, that the kind of the pressure that you need to scaling up this design, for example, and the competition. I don't know, how do you see that kind of, this is pressuring you, how you deal with that? Yeah.
So, of all the other solid state efforts that we are aware of, we don't know of a single one that has shown data indicating they can perform under uncompromised test conditions. So the data that we showed in December, where you could cycle cells for 1,000 cycles to well over 80% capacity retention at a 1 hour charge and 1 hour discharge rate of power, with 100% depth of discharge each time at 30 degrees Celsius, not 60 or 70 or 80 degrees Celsius. No one has ever shown that to our knowledge before. So that's unique. And so we don't see any other material system on the horizon that's solid state that can match that. We kind of feel like we're pretty unique there. And so our real challenge is not whether there's another solid state system that can leapfrog us, but whether we can, in fact, execute on the scale up and manufacturing challenge that we have ahead of us. So in that sense, our biggest risk really is our own ability to execute, as opposed to a competitor approach that might be out there. Material science is hard, and if someone hasn't already shown a material that has the core capabilities, it's many years, if not decades, before a brand new material can be commercially viable. We've been working on this for ourselves for about a decade, and we're only now getting to the point where we're ready to look at mass producing it, and that's after hundreds of millions of dollars raised over that period of time. Hundreds of people on the team, great customer support, great investor support. So it's just a hard problem. And the company has now raised about $2 billion, right? So this is not a problem where two guys in the garage can kind of solve it. And so we just feel like now that we've demonstrated the core chemistry, there's a unique opportunity to scale up and produce it in volume. And if we can execute on that part of it, then we really think we can make a big impact on the world of automotive powertrains.
I totally agree with you. Yeah. So maybe we go to the other question. The first question from Robert, he asks you first. I just want to say thank you for what you're doing. It's really amazing. And his question is, what does QuantumScape plan to do with the battery tech prior to being ready to EV application? Also, are battery powered for aircraft and battery powered also for Bolt, for example? Or just something like that's plans. How do you see the battery?
Yeah. Well, first of all, I want to thank Robert for the question and also for his support all to our mission. One thing that we decided early on was that rather than try to be a jack of all trades and a master of none, we thought it was more important to focus on one application and solve it well. We chose to focus on the EV automotive application because we saw that was where there was the biggest need. Today's batteries work reasonably well in cell phones and in consumer applications, but the automotive application, we feel like until you get a battery that is closer to the combustion engine in terms of range and fast charge and cost and safety, EVs will not really achieve their full potential. So we've been focused on that as our first application, which may seem a little strange because that's the hardest application in terms of all the requirements. On the other hand, the benefit of that is that because we've designed the battery for those strict set of requirements in the automotive space, once we start shipping batteries to automotive, the capabilities of those batteries apply equally well to many other sectors. Robert mentioned the aviation sector, for example. There's a lot of work going on in vertical takeoff and landing aircraft, so-called eVTOL aircraft. A battery with more energy density is critical for that space. So we could play there. The mobile phone guys will clearly love a battery that takes up less volume, so they can use more of the space of the phone for functionality instead of just battery. The grid, the power grid, right, where you need to be able to store energy to time shift the generation and dispatch of power, is another application. But all those are applications that, from our standpoint, will come, after we've already, penetrated the EV space. So we fully intend to be a multi-application battery company, but we believe that it's important to have a clear sense of focus, so you're not spread too thin and end up doing nothing well.
Yeah, great. And he also add, why hasn't been there talks, at least from what I have seen, about BRIEV small scale production phase for cell phone and laptops, as well as other consumer devices? And he said that I think that would be a powerful proof of concept for the market to see while the company works its way towards full scale production. Pretty sure if you can call the guys over Google, they would be more than willing to put your tick and their new line of Pixel phone if it's right deal is made.
I mean, I think his point is well taken. I mean, I think the consumer electronics guys and many other industry sectors would love a battery that has 50 to 80% more energy density and the ability to charge more quickly and so on, and lower cost. But I think from our standpoint, we just wanted to have the discipline of focus, right? We, rather than go after the market for EV batteries is probably, in our calculation, 20 times as big as the market for consumer electronic batteries. So given the amount of capital that's required to make a better battery, we really wanted to go after a market that was big enough to produce a decent return for our investors, so that we could justify the kind of capital that's required to do this. Having said that, like I said earlier, once we address that market, we certainly will make the battery available to other applications as well. And he's absolutely right that we're seeing a lot of interest from many other sectors outside of automotive. We're just trying to be disciplined about not getting too defocused. Volkswagen has been a huge partner of ours. They're very committed to this technology, and we take that commitment seriously. We need to make sure that we execute and deliver cells to them before we get too distracted with other sort of newer, shinier objects. I think they value that, and it's worked well for us so far to have that clear sense of focus and not be distracted by other applications. The good news is that once we address the automotive requirements, they have the most stringent requirements, because you need all of the key attributes, not just higher energy density, but you also need higher power density. You also need lower cost. You also need safety, and you also need cycle life. All the other applications we're aware of require a subset of those key attributes. So we feel like if we can meet the automotive industry requirements, then it's kind of a downhill walk from there to meet the requirements of other sectors as well.
Yeah. Maybe a quick question here about the batteries. Do you think that solid-state batteries can be designed in a way that maybe never damaged, I don't know, or maybe increase the life cycle, never being damaged? I don't know what could be lead the damage early to the batteries, for example, in EV application situation like the lifespan.
So again, one of the limitations to the cycle life of a normal lithium-ion battery is there's a chemical side reaction that happens on the anode side. So there's also one on the cathode side. So the liquid electrolyte, which is again the medium through which lithium ions move in the battery, turns out to be, it's a hydrocarbon, an organic material, and it's unstable to both the anode side and the cathode side. So there are chemical side reactions happening between that liquid and the carbon anode, as well as that liquid and the cathode particle. Those chemical side reactions consume a little bit of lithium on every cycle. And so every time you use the battery and charge it up and discharge it, you end up with a little bit less capacity than you had before you used it. That's why your cell phone eventually dies after a couple of years of use, because every cycle you're chewing up that lithium. And those are irreversible side reactions. You can't get that lithium back. Now, in a lithium metal solid state battery like ours, because we don't have any anode or any liquid on the anode, there is no chemical side reaction on the anode side. We still have a chemical side reaction on the cathode side like a normal battery does. But on the anode side, we eliminate that side reaction. And as a result, you get better life because you have that much less lithium being lost. So we do believe that these batteries have better cycle life than conventional lithium-ion batteries for that reason. Relative to safety, the fact that we don't have as much organic material, we do use an organic material in our cathode as a catholyte, but there's no organic material in our separator or in our anode. So we have less organic material. That increases the safety of our cells because there's less fuel in the battery as compared to conventional cells. Also, the separator itself, our ceramic solid-state separator, because it's a ceramic, it's very stable thermally. So an ordinary lithium-ion separator will melt and then burn at less than 200 degrees because it's also a hydrocarbon, whereas ours will be thermally stable to north of 1,000 degrees Fahrenheit. I'm sorry, 1,000 degrees Celsius, and even then it'll never burn because it's already oxidized, so it can't burn. So because of those things, we think we have both better life and increased safety as compared to lithium-ion batteries.
So we have a question also from Ryan, and asks us about what sets your EV solid-state battery technology apart from others as Panasonic or Solar Power or other developing solid-state battery platform? I don't know, you already maybe answered a little bit, but he had a lot of questions. And how does your battery density compare to the competitor, as some have suggested they are on the track of 400, for example, watt per kilogram, and how much does it cost to produce VS lithium-ion, and how these costs are brought into the consumer? I know your company on the track to sales 2025, and what are your plans potentially to speed up your overall production to beat some of this competitor in the market?
Yeah, so he mentioned a couple of specific companies, and I want to just help categorize those players because those are different types of batteries. So Panasonic makes a conventional lithium-ion battery, and again, conventional lithium-ion is defined by the fact that it has a carbon or silicon-based anode material, which takes up space and limits your charge time and adds cost. What we do is a solid-state battery with a lithium metal anode. So that's why we're different from Panasonic, or for that matter, Samsung or LG Chem or CATL, or any of the guys that make batteries today. Those are all conventional lithium-ion batteries where the lithium is stored as an ion in the carbon or silicon anode. In our case, the battery is what's called a lithium metal battery. There's no carbon, there's no silicon, there's no anode at all. And the same lithium that normally is cycling back and forth and intercalating in that carbon or silicon particle is simply forming a layer of pure metallic lithium on top of our separator. So think of it this way. A normal lithium-ion battery anode is like a basketball stadium or a football stadium where you have spectators that come in and they're all sitting in their own seats. So the carbon, each lithium ion in a conventional lithium-ion battery requires 6 carbon atoms to hold it in place. Those 6 carbon atoms are like the seat that the lithium ion sits in. In our case, it's like a stadium where we've gotten rid of all the seats, and the fans just come in and they're just standing shoulder to shoulder. You can pack a lot more people in that stadium because you don't have the extra volume or weight of the seats. So in our case, there's no carbon, there's no silicon. It's just pure lithium sitting in the anode. So that's what gives us the fundamental benefit over lithium ion. The other player that your questioner mentioned was Solid Power. So Solid Power is trying to work on a solid state system. Other players are too, like Samsung has demonstrated solid state system and so on. That system is based on what's known as a sulfide material. The sulfide is the electrolyte through which lithium ions move. And unfortunately, sulfides have not been shown to prevent lithium metal dendrites. So those systems can't work under uncompromised test conditions. They either need to be run hotter, which increases their cost, or for a shorter number of cycles, which is not practical, or at very low rates of power, which is not usable in a real car. So I would summarize by saying, relative to conventional lithium ion, like Panasonic and LG and Samsung and so on, a lithium metal solid-state battery is going to be higher energy density, faster charge, lower cost, and safer. And then relative to other solid-state systems, we're the only solid-state system that actually has been shown to work under uncompromised test conditions, which is obviously critical to be commercially viable. So we don't know of another system that has shown commercially viable performance data. So that's how we compare against both those categories.
We have also a question from Sai. Asked that, is QuantumScape planning to use 3D printer to building solid-state batteries? And do you believe that you can meet the goal earlier than expected? And what are the current challenges while ramping up production? We covered part of that, but yeah, maybe the first part of that.
Yeah, no, we don't currently plan using 3D printing, primarily because we're looking for very, very low cost, high scale production technologies. And so, 3D printing today just doesn't have the scale and the economics that we need. 3D printing is great for prototype type manufacturing or manufacturing where there's a certain level of premium you can get from the product. But for batteries, you just need to be cost is such an important driver and scale. The scale of these things is just mind boggling, right? I mean, look at it this way. So one of our partners, VW, their target, they've said by the middle of this decade is to have on the order of maybe 3 million cars a year that they're shipping. Well, 3 million cars a year would be about 3 billion of our cells per year, right? I mean, we don't know of an approach that can 3D print 3 billion of anything, basically. So you need very, very low cost processes that are what we call continuous flow. So think of it as a printing press where you have a newspaper running continuously and you're simply printing ink onto the paper. That's the kind of process that you need in order to be able to make these batteries scalably. And so those are the kind of things we're focused on. But if somebody has a breakthrough in 3D printing that allows you to make it at very low cost and high scale, we'll certainly explore that.
That's an excellent point, yeah. And I have also a question from Michelle. He asked it, how does the partnership for Volkswagen, for example, does it limit the sales to Volkswagen only? And do you plan to French non-EV use as well? I think that's something also asked before.
The question about Volkswagen is a good one. So the Volkswagen partnership has been great for us. They're very committed to the technology. They've been partners of ours since 2012. They've invested north of $300 million into the company directly. They've further committed an undisclosed sum to build a manufacturing joint venture with us to mass produce these cells. Having said all that, they do not have exclusivity on these batteries. They understood that it's important for us to build an independent company that supplies batteries to the industry as a whole, because that also drives down their costs by increasing our volumes. However, what they do get in return for that big investment and all the support over the years is the right to be first. So VW, so the first cars with the QuantumScape solid-state battery in them will be from the VW Group. But of course, the VW Group owns a number of iconic brands like Porsche and Audi, and of course, the VW brand itself. They also own Lamborghini and Bentley and so on. But those three volume brands, give us a full spectrum of, the automotive sector. High performance sports cars with Porsche, luxury sedans with Audi, and then volume, mass market sedans with VW. So one of those brands will be the first with our batteries in them. But after the first VW cars ship, we are free to work with other suppliers as well. And as I mentioned, we fully intend to be a supplier to the industry as a whole, because it's a win for everybody, including VW and QuantumScape and the whole industry. To be candid, we're most likely going to be supply constrained to start. The demand for these batteries, and in fact batteries in general, far outstrips our ability to manufacture them. So for the first few years, we will not be able to fulfill all the demand that we see out there, although we'll be working like crazy to build factories as fast as we can to meet that demand. But this is one of those situations where the demand far outstrips the supply, which is a good place to be. This is also why we have to think carefully about which customers we want to work with, whether it's the aviation sector or the consumer sector, because we already have sort of our capacity spoken for from the automotive sector. So there's not a lot of excess capacity. If we add additional sectors, we'll have to take away capacity from the automotive sector.
When will testing of 12 layers be completed? I think that's something maybe also beginning, if you can elaborate more. And how do you start build a factory?
Yeah, so we've shown 4 layers. That was earlier this year. Our target is 8 to 10 layers this year. If we can show 8 to 10 layers this year, we'll be on track to showing many dozens of layers next year, and then having cells produced in our pre-pilot line facility, which we call QS0, by 2023. And those will be, that facility will be able to produce about several 100,000 cells per year, which then will lead into our mass production, which is being done with VW as a joint venture, which is a 20 gigawatt hour facility, which is capable of several 100,000 cars per year. Right.
Question from Justin asks is, how would tooling expansion work if you decide to expanding into consumer electronic size or industrial scale batteries? Is a pardoned move. Also, since sodium may be one day be viable alternative, do you see QuantumScape one day moving towards next R&D goal in the future?
I think there again, like I said, we think the battery technology fully applies to other segments like consumer and aviation and the power grid. It's more a question of business focus. We just don't want to get distracted by other segments and then not execute on the core automotive opportunity, which is really one of the biggest opportunities in any market, frankly. We think there's probably a $500 billion per year worth of market opportunity in the automotive sector alone. So we could build a very, very big company in that space without even attacking other segments. Relative to sodium batteries, when you, again, because chemistry is hard, when you change something as fundamental as the ion that's being transported, so instead of lithium using sodium, everything changes. You need different cathodes, different anodes, different electrolytes, and that's just a massive, massive project, right? So it doesn't, until work has been done, in academic settings and in many other groups showing that there exist electrolytes for the ion, there exist cathodes, there exist anodes, and all those have been tested together relative to stability and cycle life and so on, then that's not really something that we think is going to be practical. Right now, there is no real contender for other than lithium-based batteries for the mass market. What we are doing is pretty radical already, which is we're a solid-state battery using a lithium metal anode instead of a carbon or silicon anode, and that's still, it's considered very radical, and yet it's still lithium ions being transported in the cell. So I think we don't see a lot of other chemistries that could be commercially viable, over the coming decade, other than lithium-based chemistries, and we think that solid-state lithium metal is the highest performance of those different chemistries.
Question from Kevin: what's the energy density for 4 layer cells? How thick is your separator? Has Howard Lukens, Chief Sales Officer, when merger completed? I don't know if you can answer that question.
Yeah, so I heard the first 2 questions. So we haven't disclosed the precise thicknesses of our separator. We have said that they're in the tens of microns of thickness. Yeah. And we have also said that the separator we delivered to VW in Q1, the cells we delivered to VW in Q1 as part of our VW milestone that we met, had separator thicknesses that were consistent with our commercial requirements. We know we can make commercial thickness separators. VW validated those cells already. Relative to energy density, this is exactly why we need to work to get to multi-dozens of layers in our cells. So if you look at a single layer cell with 1 cathode, 1 separator, 1 anode, the energy density of that cell will be dominated by the packaging, right? Because there's only 1 active layer and then a lot of packaging. As you increase the number of active layers, you increase the ratio of active material to inactive material, and that increases the energy density of the cell. So think of it this way: if you're trying to, ship something in a package like I don't know, apples. If you have one apple sitting in a big crate, then the ratio of apples to packaging is not very favorable. But if you fill the whole crate with apples, now you have a lot more apples as a function of the overall volume and mass of the crate. It's the same thing with these cells. Each layer stores a certain amount of energy. So as you add more layers, you increase the amount of energy as a function of the overall weight and volume of the cell. So the energy density goes up. And at our target thicknesses, we expect to have about 1,000 watt hours per liter of energy density. Today's most energy dense cells, which are the ones used by the Tesla Model 3, are on the order of 715 or so watt hours per liter. So this would be probably 50% more energy density than what you get on today's most energy dense cells. And the last point I'll make is that as lithium ion increases its energy density and lowers its cost, we get to benefit from those improvements because our cathode is the same as conventional lithium ion. So if lithium ion builds better cathodes that have more energy density, for example, more nickel-rich content, more nickel-rich cathodes, or lower cost cathode materials, we can use those same materials. But in addition to that, we don't have an anode, so we are always going to have this advantage over lithium ion, no matter where it is in its evolution path, right?
Mm-hmm. Right. So since you closed that, I have a question. Maybe the first one about what could be your aspiration or other ideas you still maybe you're thinking about it. Maybe, I don't know, about the battery after maybe 10 years. Hopefully, if you may manage to do that earlier, as soon as possible. So I don't know, when you think with yourself, what kind of thoughts or, I don't know, you have about the battery after a couple of years. Any crazy ideas? I don't know if you have.
Here's one way to think about it, right? The current chemistry that's being used today in lithium-ion cells was invented about 30 years ago, right? 1981 was the first lithium-ion battery that was introduced by Sony. And for 30 years, it's been the same chemistry with just incremental improvements, right? So now that we have this new chemistry with solid state, I would not be surprised if for the next few decades, this kind of chemistry just continues to improve incrementally to make it better and better. But again, because new chemistries are hard, I'm not overly optimistic that there's going to be a radical new chemistry that comes out. We do see an opportunity for better cathodes. For example, there are the category of cathodes known as the metal fluoride cathodes that use what's known as a conversion chemistry. Actually, in fact, we've done some of the greatest amount of work in that particular area over the last 10 years with metal fluorides. We have a lot of patents in the area, but that would still be within the context of the solid state cell that we're building. So that could give you additional benefits of energy density. So there's a lot of improvements like that we think can keep raising energy density and lowering cost, but they will all be, we believe, based on solid state lithium metal architectures.
Right. So I don't know what could be the most maybe important qualities you have gained so far. I don't know. Of course, it's not easy, but I don't know what could be for you the most one important quality.
Well, I mean, I think there's a number of key things you need to pull this off. One of the key things is you need tenacity, right? You need the ability to just keep working on the problem, in the face of challenges. It's just not easy to do new chemistries, and so you need a team that is mission driven. And we believe this team has demonstrated it's been mission driven. Many of our core team members have been around since the early days. It's kind of like climbing a mountain, where no one has ever summited before. You just don't know what kinds of challenges you're going to encounter on the path, and need a team that's capable of basically, being willing to face those challenges and find ways to overcome them. And there's constantly new challenges being thrown at you. At the end of the day, building a new battery is different than, say, writing a piece of software, because it has to comply with the laws of physics, and so you can't just will a solution into being. You have to really find a solution that exists in nature, and that's hard. It requires a lot of experiments and a lot of tenacity, as I said, willingness to deal with new challenges every day. We're lucky to have a team that does that, and I think with a team like that, we feel like we have a good chance of completing what we started here and taking these batteries from lab demonstrations into production shipments. And at that point, I think we'll really have a chance to make a big impact on emissions, which of course is our key goal.
Okay,
thank you for the time, Nora. Appreciate it.
So,
fantastic.
Thank you, Jagdeep.
Thank you so much, Marva.
Okay.
Take
Bye.
care. Okay.
Thank you. Bye. Bye.